Assalamu alaikum everybody. Lab number 10 is about graphs. So as usual, I expect you to download the zip file from Blackboard. You will see it here under lab 10. I should emphasize actually lab 10 is very long. For that reason, we normally break it into 2 labs. So this is why you see here we have lab 11, more on graphs, but without any link. Okay, the content is the same as lab 10, but the material is being divided into 2. Half of it will be done as lab 10, and then the other half will be lab 11. So we're going to be doing the labs on graphs over 2 weeks. And I will explain the division when we look at the document. Okay, so the document, as usual, it states the objectives, which is to learn how to implement graphs using one of the methods that we outline in the lecture, which is adjacency list. So it's going to use linked list. We're going to also learn some of the basic algorithms of graphs, thereby using the implementation of graph that we have implemented here. Okay. Now the first thing I'm going to do, I will spend some time to explain the implementation of graphs using the class graph as list, because we didn't explain anything about the implementation in the lecture. Mainly we focus on the concepts. So this will take a little while, but don't mind, given that this is for 2 weeks actually. I will not have to come back in the remaining part to explain the class. It will have been already explained in this first part. So we'll see a class called graph as list, and inside it has 2 inner classes: vertex to represent a vertex of graph, and edge to represent the edge of a graph. And then as usual we have a test class, a main class that will allow us to test the graph as list. Okay, so I will go to NetBeans and try to explain as much as possible how we implement this graph as list. Okay, this is the graph as list class. After you unzip the file, you open the lab 10 project. It's the same project that you're going to use for lab 11 as well, but as I said, some of the tasks will be done in this present lab, and the second part will be done in next week. Okay, the graph as list class has a number of variables which we should take note of. It has a variable to represent the total number of vertices in the graph, so like the size of the graph if you like, and the number of edges. Okay, and then it has these 2 important arrays. As we recall from the definition of graph, it consists of 2 sets: a set V of vertices and a set E of edges. Now in this implementation we are representing the vertices using an array of vertex. Okay, a normal array of vertex. As I said, the vertex class is explained here as an inner class. I mean, it's implemented here as an inner class, so we'll talk about it. But this variable vertex is simply an array containing objects of that class. So the vertices are going to be represented as objects of vertex, and they will be stored inside this array called vertex. The second set is the set of edges. And as I explained in the lecture, this is going to be represented as an array of linked lists. Linked list of what? Linked list of ages. Okay, the variable name is called adjacency list because we are adopting the adjacency list representation method. And as we mentioned in the lecture, maybe I can show you that slide briefly. We're going to use an array, but the content of that array are linked lists. Okay. Now inside this linked lists, you will have edges that are emanating from the corresponding vertex. I hope that's clear. We have an array of linked lists, and the linked list will contain edges. Now here you have to understand the plan. Maybe I can show you what we are expecting to do actually. That array will contain linked list of edges. Now which edges? Okay, so in cell number 0 of that array, we're going to have all edges emanating from 0. So if you look at our first example here in the lab document, this is our first graph, which we call GA. We're going to test it later. So this is an undirected graph, and you can see that for vertex 0, we will have 3 edges emanating from it: 0, 1, 0, 3, and 0, 4. Therefore, in our array of linked lists, if you go to linked list at 0, you will see these 3 edges. Those are the edges emanating from vertex 0. Okay, that's what you are seeing here: 0, 1, 0, 3, and 0, 4. Okay, if you go to vertex 4, for example, the linked list in this particular cell will contain again 3 edges. What are these edges? All the edges that emanate from 4. Okay, so if you look at the diagram, they are 4, 0, 4, 1, and 4, 6. Okay, so that is basically how we will be representing the edges. So in terms of our data structures here that we are using to represent the graph, this variable adjacency list will represent that array of linked lists of edges. Okay, and then this simple array will be an array of vertex. The other variable that we need is a Boolean variable that we can use to know whether the current graph is directed or not. Okay, so these are the variables. Before we look at the inner classes, let us at least explain the constructors of this graph as this class. So the constructor here will receive 2 inputs: the size of the graph. By the size of graph here, we mean the number of vertices. How many vertices will the graph has? And actually it is based on this that we will know the size of this array and also the size of this array. Okay, and then it will also receive a Boolean variable telling it whether the user wishes to create a directed graph or an undirected graph. So if this is true, it means he will want to create a directed graph. If it is false, he will want to create an undirected graph. Okay, so and as you can see, the constructor here is simply trying to initialize these variables. Obviously, the Boolean that is directed will be true if this variable is directed. So basically, it's just saying assign is directed to this Boolean variable received. Okay, now that we know the size of the graph, we can create this array. So it is simply going to be new vertex array of the given size. We can also go ahead and create this array. It is going to be new array of linked lists of the given size. Okay, so the size of that array will depend on the size being given. So here, for example, the size was 9. As you can see from the diagram, there are 1, 2, 3, 4, 5, 6, 7, 8, 9 vertices. So it's going to create an array of size 9, and that array will be indexed from 0 to 8. Okay. Now that creation doesn't create the list inside the array, only create the array itself. So at that point, the values inside the array are all null. That is why we need a loop to actually initialize those linked lists to something not null. Okay, so this is not enough to create the linked lists. It is enough only to create the array. So now this loop says run from 0 to the size of the array, and for each element of that array, create an empty linked list of age. Okay, so now the initialization is complete. We created an array of linked lists, and we have now gone through each cell of that array and store inside an empty linked list of ages. So this is basically what this constructor will do. The second constructor here is simply saying in case the user did not supply a value for the directed, we should assume he's going to create an undirected graph. So we call the same constructor sending false as the value of directed. So it will do the same thing here. The only difference is this is going to be false. So its directed is going to be false. Okay, we will come back to the methods of the graph as list class later, but for now let us try and explain the two inner classes, vertex and age. Starting with vertex. So vertex is a class intended to represent a vertex. Okay, what are the properties? A vertex has two properties. An ID, we want to be able to identify each vertex with a specific ID. So we have an integer variable here for the ID. Now a vertex may also have a weight, okay, a certain value. It could be a label for that vertex if you wish, or it could be an actual value like we saw in the Dijkstra's algorithm. The resulting graph will have a cost indicating the cost of reaching that vertex from the starting vertex. So we can use this weight for anything, either label. This is why we are putting it here as type object, because object can hold any type of data. So we just call it weight. It could be a label for the vertex A, B, C, D, or it could be actually a value, a boolean, a double value or an integer value, it doesn't matter. Okay, so a vertex will have these two variables, and the constructor here is just initializing the two variables with the argument received. Okay, so ID equal to V, weight equal to WT. In case there is no weight, so we just make it null. Just call the other constructor and assign null to weight. Okay, so those are the two constructors for a vertex. A vertex has accessor methods, get ID that will return the ID, and get weight that will return the weight. Okay, it has equals method. Okay, so it's going to compare the current vertex against another vertex. So the first thing to do is to typecast the other vertex which will be received as an object. Remember, we cannot change the signature of equals. The parameter here is always an object, even though we know what will be supplied is another vertex. So that object, typecast it to vertex and save it in the variable other. The question is this other vertex equal to the current vertex? We are saying return true if their IDs is the same. So return ID equal to other.id. Here ID means this ID, the ID of the current vertex. Okay, if you wish, you can say return this.id equal to other.id. So two vertices are equal if they have the same ID number. Okay, those are the simpler methods. Now, in addition to this, a vertex has four other important methods. Okay, of course, there's a toString. We'll come to explain it later. But these are very important methods. Two of them related to edge and two of them related to vertex. The idea is we should be able to ask a vertex, please give us your incident edges. Okay, we explained the difference between incident and emanating edges in the lecture. For undirected graph, the two are the same. Emanating and incident are the same. But for a directed graph, the get incident edges will return those edges that terminates at the vertex, while this one will return the edges that emanate from the current vertex. So to give you an example, let's use a directed graph. So if you look at GB, if we ask tree, what are your incident edges? If we ask the vertex tree, what are your incident edges? It should say my incident edges are 1, 3 and 0, 3. So those edges that terminate at 3 are called edges incident tree. Okay, if you ask the same question to vertex 4, it will say my incident edges are 6, 4, 1, 4, 3, 4. I think that's all, 3 of them. Okay, so that's what the method get incident edges is supposed to do. It's a method of a vertex. Okay, if we ask a particular vertex, what are your incident edges, it will give us a list of edges, all those edges that terminate at that vertex. Okay, now we can also ask a vertex, give us your emanating edges. So those are edges that will emanate from that vertex. In this case, for example, it's going to be 4, 2 and 4, 5. For 3 is going to be 3, 2 and 3, 4. So those are what these two methods are supposed to do. You can see get incident edges is returning an array list of edges. This array list will contain all the edges incident to the current vertex. And similarly here, get emanating edges will return an array list of all edges emanating from the current vertex. Now the question is, how do we implement these methods? Okay, now the good news is in the graph class itself, in the graph as lists, there is a similar method inside the graph as list. I will go and show you the method. The same name, get incident edges, but this time it has a parameter. Yeah, get incident edges will receive a parameter int v1, and it will return the edges incident to vertex whose ID is v1. Similarly, get emanating edges, it will receive a vertex v0, and it will return the edges emanating from that vertex. Now I will explain these methods later. I'll come back to them. But to implement similar method inside the inner class vertex, we are just calling this method of the outer class. Okay, so the question is, how do you call a method of an outer class from an inner class? How do you call the method of graph as list from inside the vertex class? Okay, this I'm not sure if you have learned from your previous course, so I'll try to explain it. Okay, see, when we say get incident edges and we provide the ID of the current vertex, we are calling a method of the outer class to give us the edges emanating from the vertex whose ID is this, which means the current one. Now, how do we call that method? If we just say this, or if we just call the method get instant edges ID, it means automatically this. And you're calling a method without any reference actually means reference. But this, in the context of the inner class vertex, it means reference to the vertex class. But this method is not a method of the vertex class, it's a method of the outer class graph as list. Therefore, if you want to really call a method of the outer class, you have to give the name of the class. So you say graph as list dot this dot method. Okay, so this is how to do it. If you want to call a method of the outer class, you have to mention the outer class, and since the method is an instance method, you have to say dot this and then dot method. All right, so basically the vertex class is relying on the outer class to get its own incident edges. Okay, we're going to receive an array list from that method, and that is what we're going to return. Get emanating edges is similar. It is calling the method of the outer class, providing it the ID of the current vertex. Okay, it will return an array list, and that is what we're going to return. I will explain these two methods of the outer class, as I said, later when we look at the graph as list class itself. Okay, the next two methods are related: get predecessors and get successors. So here we are asking a vertex like 3, who are your successors? Now, successor of a vertex is not an edge, it's actually another vertex. All the vertices adjacent to 3 are referred to as its successors. But here you have to be careful. The successors in the case of directed graph are not all the connected vertices. Okay, for example, 1 is not a successor to 3. Rather, it is a predecessor. From 1 we go to 3. The successors, we get them by following the emanating edge. From 3 we can go to 4 based on the arrow. From 3 we can go to 2. So the successors of 3 are actually vertex 4 and vertex 2. Okay. The other method we will see is returning the opposite. It's asking what are your predecessors. So to know the predecessors, we use the incident edges. Okay, the other vertex at the end of this incident edge is a predecessor. From 1 we can go to 3, so 1 is a predecessor to 3. Similarly, from 0 we can go to 3, so 0 is a predecessor to 3. But for an undirected graph, the two are the same because the arrow here can go either way. So if you want to know what are the successors of 4, they are 1, 0, and 6. What are the predecessors of 4? Also 1, 0, and 6. Okay, so that's the difference between successors and predecessors in the context of directed and undirected graph. Now the other point to note, if you observe, probably you have observed already, successors are obtained using emanating edges. So if you have 1, 2 emanating edges, definitely you will have 2 successors. Just follow the edge, reach the other end, the vertex you're going to get is a successor. Similarly, if you follow this emanating edge, you're going to get a successor. So if you have 2 emanating edges, you will have 2 successors. Similarly, predecessors are obtained from incident edges. So if you have 5 incident edges, you're going to have 5 predecessors. In fact, this method is being implemented based on that exactly. So get predecessor, we know that we're going to get predecessor from incident edges. So the first thing this method does is it calls get incident edges. Get incident edges and save your result as an array list of edges, okay, called incidents. Now we're going to go through the edges inside this array list one by one, and for each one of them we will be able to find one successor, or one predecessor rather. Okay, so we define a new array list where we will store our predecessors, this time an array list of vertex, because predecessors are vertices. So as you can see, the method is returning an array list of vertex. So create an array list of vertex called preds and initialize it with an empty array list. Now go through all the incident edges that we obtain from get incident edges using for each. For example, you can say for each edge in the incidents. Okay, now there is a very nice method of edge. We will see, we will come to it when we look at the edge class. This method, what it does is, if you give it one vertex for which the edge is connecting, it will give you the other. Okay, it is called get met. What I mean, for example, if you ask this edge, please, what is the met of 0? It will say 3. Okay, please, what is the met of 3? It will say 0. We will see the method get met in a moment. Okay, so there is a method of an edge called get met. You give it one vertex corresponding to one end of the edge, and it will give you the other end. Okay, so the idea is we already got the incident edges. So all we have to tell it is, please, who is my met? This edge, who is my met? It will tell you 1. So you will conclude 1 is a predecessor to me, me being vertex 3. Similarly, it will ask this incident edge, please, I am 3. Who is my met? It will say, well, your met is 1. So you will conclude 1 is therefore a predecessor. This is basically what that loop is doing. Because for each edge in incidents, ask, who is the mate of me? This means the current object, right? So who is the mate of the current object? Okay, this get mate is a method of this edge that we just obtained from the array list of incident edges. So Mr. Edge, who is my mate? So it will give you a vertex. The vertex that you get is a predecessor, so add it to the list of predecessors. So preds.add edge.getMate. Then go and get the next edge and do the same thing. So by the time you finish this loop, you will have obtained the list of predecessors. And that is what we are returning here. Okay? In the same way, get successor will return the successors by first obtaining emanating edges. So it calls the get emanating edges, save them in an array list of edges called emanatings. Define a new array list of vertex called successors. Okay, and then loop through these emanating edges. For each edge in the emanating, ask it who is the mate of the current vertex. The mate of a current vertex is definitely a successor. Since this edge is an emanating, the vertex is a successor, so add it to the list. At the end of the loop, you return all the successors. So these are the 4 important methods that a vertex will have. The toString here is simply printing the information about the vertex, its ID, its weight if the weight is not null, surrounded by V followed by an opening bracket and a closing bracket. Exactly as you can see here in this sample output. So a vertex will be V, opening bracket, and the vertex ID and closing bracket. In case the vertex weight is not null, it will also appear here within the bracket, separated by, as you saw there, separated by comma. Okay, so ID, if there is a weight, comma, weight, and then before all of this you have V, opening bracket or opening braces, and a closing one. So append all of this into one string and return it. This is basically what the toString is doing. So that is the vertex class. Let's look at now the edge class. The edge is comparable. So in addition to all the methods we're going to see, we have to implement the compare to method. We are making it comparable because it can be used, for example, when we come to discrete algorithm. I'm not sure whether I'm going to show you the discrete algorithm implemented, but this is why basically the class is being comparable. Because if you recall, in discrete we have to order the edges according to their weight and choose the minimal one and finalize it before we move to the next round. Okay, so that's just to give you an idea why are we requiring edge to be comparable. But I doubt whether we will use that in the examples I'm going to show you. Okay, now what are the variables of an edge? 3 variables. Every edge will have 2 IDs corresponding to the IDs of the vertices it is connecting. You remember, an edge is supposed to connect 2 vertices. So among its properties will be V0, which will be the ID of one of the vertex or one of the vertices, and V1 of the other vertex. It may have a weight in case the graph is a weighted graph, or it may not. So this could be null, but this and this cannot be null. Okay, and the constructor is simply initializing those 3 instance variables. Okay, now in case we didn't receive a weight, so this second constructor will initialize weight to 0 because the variable is there anyway. It's of type double, so we are giving it the value of 0. Okay, there are 3 accessor methods: get V0, get V1, and get weight. However, here you have to understand, get V0 is not only returning the ID V0, it's actually returning a vertex with that ID. So get V0, it will return a vertex. Similarly, get V1 will return a vertex corresponding to this ID V1. Okay, so how does this work? I should inform you, actually, the other array that we mentioned, the array of vertices, we're going to store the elements very cleverly inside that array. The array is going to be indexed from 0, as you can see from that output. Now we're going to be storing the elements according to their ID inside that array. In other words, the age with ID 0 is going to be stored in cell number 0 of the vertex variable, vertex array. Okay, cell number 1 will contain a vertex whose ID is 1, and so on and so forth. So once you know the ID of your vertex, we know where to go in the array to get it. Okay, the elements are stored in this array based on their IDs. So we don't just randomly store the vertices. They are stored according to their ID. So the vertex with ID 0 will be stored in cell 0. Vertex with ID 1 in cell 1. Vertex with ID 2 in cell 2, and so on. Therefore here, just by knowing the ID, we can go to that array and locate the vertex corresponding to that ID. Okay, the ID is V0. So to get the actual vertex, we go to the array at location V0, locate the vertex and return it. Okay, and similarly for get V1. Okay, we don't just return V1, no, we go to the array corresponding to cell V1 and get the actual vertex object, and that's what we are returning. You see, the return type here is not an int, it's a vertex, but vertices are stored inside this array. Okay, but the get weight simply return the weight. There is no array involved, just directly return the variable. And this is our interesting get met method that we discussed earlier, which I said we will see when we come to the edge class. So the method get met, you give it a vertex and you expect it to return another vertex. Okay, so this vertex is not any vertex, it's vertex for which the current edge is connecting. So actually you have to check to make sure, is it not, you make sure it is not just any random vertex. It has to be a vertex for which this edge is connecting. That's why here we need an if statement. So the vertex we receive, we check what is its ID. So if v.getId, is it equal to one of our IDs, v0 or v1? Okay, if it is one of them, then we can answer the question. Otherwise, we cannot. It's an invalid vertex. Yeah, so that's the idea. If v.getId is equal to v0, then the met is going to be the vertex corresponding to v1. So again, you don't just return v1, you have to go to the array at location v1, locate the vertex and return it. Similarly, if the ID is v1, then we're going to return the vertex corresponding to v0. This is a met. If none of this if statement is true, then we're going to return null. Sorry, the vertex you give me as an edge doesn't correspond to me. I don't know this vertex. That's what we are saying. So invalid argument. Okay, we could have thrown an exception here, maybe better. But to make the code easy, we just return null. Okay, so this is what getMet is doing. For any current edge, if you give it a vertex, provided that vertex corresponds to either its v0 or v1, it will be able to answer the question and return the other one, the met. Okay. Then we have is directed. An edge should be able to tell us whether it is an edge or not. So this is again very similar to what we saw in the vertex class, because the graph itself has a method is directed. So for this edge to answer the question whether it is directed or not, it is simply saying return true if the edge is an edge of a directed graph. An edge of a directed graph definitely is directed, otherwise it is not. Okay, so that's all we are doing here. Call the is directed method of the outer class. If you get true, return true. If you get false, return false. Okay, so an edge is directed if its enclosing graph is directed. Okay, we mentioned that the edge is comparable. So this is the implementation of the compare to. We're just going to compare the weights of the current edge and the other edge that we're going to receive. Okay, and if the current one has a smaller weight than the other one, then we return -1. If it is greater than the other weight, we return 1. Otherwise, we return 0. So the comparison is based on the weights of the two edges, because that's what we need actually in the discrete algorithm, or as you may see in the Prim's algorithm for spanning tree, which we'll discuss in the next lecture. All right, there is equals method. How do we know if two edges are equal? Well, simply if their V0s are the same and their V1 are the same and their weights are the same. Okay, so only if all the properties are the same, then we can say this edge and the other edge are the same. Okay, the final one is the toString. How to print an edge as a string is very similar to the vertex. We start with E, opening braces, followed by V0. Now, here it depends whether the edge is directed or not. If it is directed, we will use an arrow before we connect it to V1. If it is not directed, we simply use dash dash. So as you can see in this output, we are using dash dash, because this graph actually is representing this first one here. It's an undirected graph. Okay, so that's the idea. Okay, so you put that, and then in case there is a weight, you're going to add it following a comma before you close the braces. So that's how to print an edge. Okay, E, brace, V0, dash dash, V1, and close the brace. So this is how to print an edge. In case it is a directed graph, this is going to be an arrow, not a dash dash. Okay, that's exactly what the toString there is doing. Okay, so that brings us to the end of the methods of an edge. So really the most important method there is getMet. The rest are more or less accessor methods. Okay, now let's start to look at the methods of graph. Okay, the graph has a number of methods. Some of them are trivial, but some of them require closer look, especially the traversal methods. Okay, so the first ones here are just accessor methods. We remember there's a variable number of vertices, number of edges, Boolean variable is directed. So this accessor method will simply return the values of those variables. Okay, there is a visit method, just like we have in trees. To visit a vertex, simply print the vertex. Okay, so we'll receive a vertex V and print it. Okay, how do we add I think before we look at adding an edge, okay, there are methods to help you add an edge and also to help you get an edge. I want before that to look at the add vertex, because I think it's important to understand the add vertex. Okay, so this is the add vertex method. Here, remember, a vertex has an ID. Now we're going to make sure that the user is not the one to give that ID, because if he does, then he may give two IDs to the same vertex. Rather, the program itself will be generating the IDs. Okay, so let's look at this first constructor here. We want to add a vertex to the current graph. And remember where the vertices are stored. They are stored inside the vertex array. Okay, so what we do is we're gonna give the first vertex added. We're gonna give it ID 0. And if you remember, number of vertices initially is 0. So once you create a vertex and add it to the graph, you're going to save it in position 0. This is 1. 2, you're going to give it ID 0. You see, when you say new vertex, number of vertices, you are giving an ID. So initially this value is 0. So create a vertex whose ID is 0, whose weight is what is given here. Okay, so we have a vertex with ID 0 initially. Now, where are you going to save this vertex? Inside the vertex array at the corresponding ID, so at 0 initially. But immediately after this, we're going to increment our number of vertices by 1, because now we have 1 vertex. Okay, so number of vertices will be incremented by 1. Next time you call add vertex, it will create a vertex with ID 1, because now number of vertices is 1. Okay, save it in position 1 of the array, and then increment the number of vertices to be 2, because now we have 2 vertices, like that. So this is basically how we will be able to add the vertices. Okay, by not allowing the user to give the ID, we will be using this variable number of vertices to actually represent the IDs. So initially 0, then 1, then 2, and 3, and so on. So if you add 10 vertices, they will have IDs from 0 until 9. Okay, number of vertices will return 10, of course, because it is only after we add that we increment it. Okay, good. Now, most of the time, you don't really have weight for your vertices. So in that case, you will be calling this method. Now, add vertex here doesn't need any parameter, because if we don't have weight, it is only the ID that is left. But we don't want the user to give the ID. We want the system to give the ID. So this is no parameter, therefore. So you call the other method with null as the value of the weight, and it will behave exactly as we explained. Okay, so this is the add vertex method. We can now, well, maybe before we go to add edge, I can quickly explain this get vertex. So after adding a vertex, suppose the user wants to get the vertex corresponding to a particular cell. So this cell, of course, remember, will also match the ID. So it could be give me the vertex corresponding to this ID, or give me the vertex corresponding to this cell in the array of vertices. Either way, the same meaning. Now, we cannot guarantee that the user will give a valid ID, so we have to check if V is less than 0, or it is greater than number of vertices minus 1, then definitely it's an invalid ID, so we return null. But if it is within that range, just go to the array of vertices corresponding to V, obtain the vertex there, and return it. Okay, so this is what the get vertex is doing. there is one method here that is returning all the vertices. Basically, just return the array of vertex. The array of vertices called vertex. Okay. Type. Let's go back to age now. How do we add an age, and then how do we get an age? So again, there are two versions of the method. In first case, we have as input v0 and v1 and weight as well. So the age is full. It's corresponding to IDs and also the weight. So now how do we add an age v0, v1? Remember, the ages are being stored in the other array called adjacency list. This array has already been created. To add an age, we just need to call the add method. But the question is, where do we locate this particular array list, given that our adjacency list array has many linked lists? Okay, so suppose we receive age with ID 1, 2, where V0 is 1 and V1 is 2. In which of this linked list should we add the age? Basically, it's going to be in the linked list corresponding to 1. Okay, because as you can see, all the edges here are starting from 1. 1, 0, 1, 2, 1, 4. So go to location 1 and then create a new edge with value 1, 2 and add it to the list. That is exactly what the method is doing. It's saying new edge v0, v1 weight, but add it where? At adjacency list at v0. So adjacency list at v0 dot add new edge v0, v1 weight. Of course, after adding the age, you have to increment the number of ages. So this is how to add an age. In case we don't have a weight, only v0 and v1, we will call the same method, but with 0 as the weight. Okay. How do we get an age? So we give the system or the graph object two IDs, and we want to return the age corresponding to two IDs, v0, v1. Very similar to the way we get a vertex. First, you have to make sure that both these two IDs are valid. Okay, for example, if your graph has only 8 vertices, 9 vertices, as we saw in our diagram here, there are 9 vertices. So the last possible value for a vertex is actually 8, because the vertices will be numbered from 0, 0, 1, 2, and so on. So suppose the user say, give me vertex number 1, 9. Definitely that is an invalid vertex, because there is no vertex with ID 9. Okay, so the first thing you have to do is check that the given IDs are valid. So if v0 is less than 0 or greater than number of vertices minus 1, or v1 is similarly, return null immediately. The age is invalid. This age doesn't exist in the current graph. Otherwise, all you have to do is go to the adjacency list, which contains the edges, at this particular location, v0. Okay. Now, as we remember, the linked list in the Java library doesn't have a find method. Otherwise, it's easy to actually locate and find a particular element using one traversal. The Java's linked list cannot do that. First, you have to get the index of the element you are looking for, and then you now use that index to locate use the get method to locate the element corresponding to that index. So we have to do it twice, because we are using Java's linked list, not our DLL Java's linked list doesn't have find. If it has, we could have just used one call, but there is no such method find. So what we do here, we go to cell 0 in the adjacency list and ask it, please give me the index of an edge v0 v1. Okay, so for example here in our output, this is why I run the program so that I can show you what it means. If you come here and say this linked list should give you the ID of an edge 41. Sorry, the index. Give me the index of an edge 41. So it will scan and say this is number 0, this is number 1. So it will tell you, okay, that index is 1. All right. So we got 1 as the index. Now that we know index is 1, of course we have to check, is it a valid index? Because if the edge doesn't exist, we're going to get -1. And the index will return -1 if the edge that you search doesn't exist. So that's the first thing you have to check. If index is not -1, now we can call get method, give it the index, and it will return to you the edge. So return adjacency list at v0 dot get, and then you give the index. So now we're gonna get the edge. This is how to get an edge. Okay. Okay, next method is add vertex. This time we have discussed the add vertex. Sorry, we have discussed all these 3 methods: add vertex with a weight, add vertex without a weight, and we have also seen get vertex and get vertices. So we have done all the basic methods. Now let's look at these 2 important methods that we skipped earlier: get incident edges and get emanating edges. Okay, let's start with the get emanating edges. So the graph, not the vertex class now, the graph itself, it receives a vertex ID and it wants to return the edges emanating from that vertex whose ID is this. How do we do that? Very easy. From our representation here in the run, we know that this linked list that is in cell number 0 contains all the edges that emanate from 0. So 0, 1, 0, 2, 0, 3, 0, 4. Similarly here, cell number 6 will have all the edges emanating from 6, 6, 3, 6, 4, 6, 1. So actually all we have to do is come to the array at the location of v0 and return all the elements here. They are the emanating edges from vertex 6. Do you get the point? Yeah, so this is exactly what we are doing here in the code. It says, so first we create an empty array list of edges. Okay. Then go to adjacency list at v0. You're gonna get a linked list. Now there is a good news here. We have never seen this method before, or I never explained it to you before, but actually it's a very useful method. You see, linked lists, in addition to add method, they also have add all method. Add takes a single element, like one edge, and add it to a linked list. But suppose I have another linked list containing the same type of element that I want to add. Okay, I don't have to use a loop to go through them one by one and say add this, add this, add that. Okay, because that's another way you can do it. You can say for each edge in this list, emanating.add edge. No need to use a loop. Just say emanatings, which is this empty list that you just created, dot add all, and you give it the whole of your list. So if you give it the whole of this list, automatically it will get the ages one by one and add them to your results. So it will add 863, 864, 867, and so on. So this is the idea of add all. No need to do a loop. It will take the whole list and put its content for you one by one. So that's how we get the emanating ages from V0. Just go to adjacency list at V0. It will give you a list of emanating ages. Add them to this new array list and return your result. Okay. Add all is applicable to all Java data structures. You have it in linked list. You also have it in array list. It's a very useful method. Okay. Next is get incident ages. Now, get incident ages, unfortunately, is not straightforward like get emanating ages. Because again, if you go back to our example, the incident ages, they are not in one linked list. For example, if you want to know all the ages emanate, are rather incident to 1. Here there is 0, 1. There is 2, 1. And there is 4, 1. Okay, as you can see from our diagram, ages incident 1 are 0, 1, 2, 1, and 4, 1. So 3 of them. But they are not in one linked list. Okay, they are in different linked lists. So we cannot use add all this time. We have to search the list one by one to get the corresponding age and add it. And that's what we are doing here. So first of all, create an empty array list called incidents. This is the one we're going to populate and return it. Now you need a loop, because you have to go through that array list of linked lists, array of linked lists from 0 until number of vertices. So for int v0 equal to 0, as long as v0 is less than number of vertices, v0 plus plus. So what do? We go to that linked list at v0 and ask it, what is the index of an age that ends in v1? Okay, this is the v1 parameter we receive. I want to know all ages incident to 4, for example. Okay, so it will ask that linked list, do you have an age that terminates at 4? It is going to give you a number because you're asking index of. So save that number as index and now check, is it not -1? If it is not -1, it's a valid index, so you can now use the get method. Get me the age corresponding to this index in the particular array list, and then add it to your list of incident ages. Okay, so this is basically how the get incident ages is implemented. You have to search through the list one by one to get the ages incident to the particular v1. All right. Now we have two main important methods to discuss. They are depth first and breadth first traversals, and they are exactly as we discussed them in the lecture, only that in the breadth first, rather in the depth first, instead of using stack, we're going to use a recursion. So it's slightly different, but breadth first is exactly the same as we discussed. So maybe I will explain breadth first first, because it will be very familiar to what you already know. Okay, so breadth first will receive the index of the starting vertex. Okay, if you recall, it uses a queue. So also we need to use a Boolean array to track the vertices that were enqueued before, so that if they are enqueued, we don't enqueue them again. Okay, so this is a Boolean array called enqueued. Okay, the same number, the size of that is the same as the number of vertices. Initialize each cell of that Boolean array to false. Okay, so we have our Boolean array initialized to false. meaning we have not enqueued any vertex so far. Good. Next, create a queue. So this is why here you see there is an LLQ, because we need it in the breadth-first traversal. So create an empty queue of what? Vertices. So LLQ of vertex, Q equal to new LLQ of vertex. Now before the loop, push the starting vertex. So we say Q.NQ vertex at start. Remember, start is just the index, not the real vertex. To get the vertex, you have to go to the array. So Q.NQ vertex at start, and mark that as visited. Enqueued at start becomes true. Right? Now we start a loop. While Q is not empty, we do three things. Dequeue a vertex from the queue, so it's going to return to you the front one. Save it as V. Visit the vertex. Remember, no question asked in breadth first. Just visit it. Dequeue and visit. Next, we're going to enqueue the successors of this vertex. Well, we just saw that a vertex has a method called Get Successors. It will give you an array list of vertices. So get the successors of these vertices, and then you go through a loop. For each successor in the list of successors, get the ID of that successor and check whether it was not enqueued before by checking the Boolean array. So if not enqueued at this ID, so you go to the array corresponding to the ID and see if the value is not false. Okay, so I mean it's not true. If not enqueued, meaning we never enqueued it before, in that case Q.NQ successor, and mark it as enqueued now, so that next time you don't enqueue it again. Okay, so this is exactly what we saw in the lecture and in the animation. Okay, we get the successors of the corresponding vertex and then check if they were never enqueued before, enqueue them, and now mark them as enqueued so that you don't enqueue them next time. This is exactly what we discussed. All right. The last method is the depth-first traversal. Here we are doing it with recursion, so it makes it even more easier actually to code compared to the one using array. So it has two versions. The first version, which is the auxiliary method actually, is the one the user will call. That's why we'll call it public. So it will receive the starting vertex. What it will do here is it's going to create an array of the Boolean. So it creates an array, this time not of enqueued but of visited, because in depth first we only visit if not visited before. So I create a Boolean array, initialize its cells to false. Once you are done with that, call the recursive version. So the recursive version will receive the same starting vertex along with the array. So it's not doing anything in this method other than creating the array, initializing it to false, and then calling the recursive one. Now the recursive one, as you can see, it is receiving those two arguments, int start and Boolean visited. The first thing it does is it checks. If visited, start, return immediately, nothing to do. So if the vertex at this point is visited, nothing to do, just return. Otherwise, it will visit the vertex at start, mark it as visited, and then do a recursive call. Okay, first of all, it gets successors. So visit the vertex at start, mark it as visited. Now get all its successors. Get the successors of that vertex, save them in an array list, and then do a recursive call with each one of them, provided that one is not visited before. Okay, so for each successor in the set of successors, okay, check. Get the ID of that successor first, and then check. If that vertex corresponding to that ID is not visited, start another traversal from that ID. Okay, again passing along the array of visited. So this will completely start another traversal from one of the successors. Okay, delaying the rest of the successors. Okay, again it will go deep. Take one of the successors of that one and keep going. So you can see how it will do it depth first actually. But eventually it will be able to visit all of them. Yeah, so this is basically how the depth first traversal will work. It is doing it recursively. And this is the end of the implementation of this particular class. Of course, there is a toString here, which will print the graph exactly as you are seeing it here in this output. Okay, so how is it doing it? It defines a string initialized to empty, and then it goes through that array of vertices. Okay, so for I from 0 to number of vertices, okay, get the vertex from the array of vertex. Okay, so we add that to S followed by a column. So as you can see in the output, we get the vertex and a column. Now get the linked list of edges emanating from that. So this is what we're going to get from the other array. Okay, so that's what is happening here. We say add, after separating by a tab, add the linked list at I to the same linked list. Now add a new line and then repeat. So by the end of this loop, we will have a string representation of our graph exactly as you are seeing here.